Okay, hey everyone. Thank you all for showing up to tonight. My name is Jeffrey. I am a PLTL leader for CHEM 1312, and tonight I'll be leading you all through the first student success member CHEM 1312 exam review. So this portion will consist of lecture, and afterwards we will talk about practice problems in the breakout rooms. Okay, first we're going to talk about chapter 13, the physical properties of solutions. We're mainly going to go over what is a solution, what factors that affect the rate of solution formation, and also the math involved. Okay, so first let's talk about what a solution is. So these terms may seem simple for many, but it's a really good idea to keep the basic definition in mind when we're talking about when we're doing math and we're using formulas. Okay, so what are solutions? Solutions are homogeneous mixtures of two or more substances. A good example I like to relate to is Kool-Aid. If you remember that drink when you were really younger, please don't change the slides, y'all. Thank you. So usually Kool-Aid, it consists of a solvent, which is water. It's a medium in which solids are mixed. And there's also the Kool-Aid itself is a solute, the component that is dissolved in the solvent. And we were talking about solubility, referring to the amount mass of solute that forms a saturated solution with a given mass of solvent at a specific temperature. Right on the right, we have different types of solutions. First, we have the unsaturated solution, a solution in which more solute can dissolve. The saturated solution, a solution in which contains the maximum amount of solute. And a supersaturated solution, which is a solution which contains more than the maximum amount of solute. Usually this is super cool in the lab, and you can tell by the different how it looks in the solution, like the picture on the right shows. Okay, so let's talk about how a solution is formed. First, this is all about entropy, which can be determined by the magnitude of each of the steps by formation. So the first step, there are 3 steps. The first step is the disruption of solute, which is endothermic, and that kind of makes sense because when you have to first disrupt the bond, so you have to supply kinetic energy or heat to it, as shown here. This is marked by a delta H or the change in heat is positive because you're gaining heat. Second is the disruption of the solvent bonds, which is endo, and you have to supply heat for that again. Third is the formation of a solute in the solvent, which is exothermic this time. If steps 1 or 2 are greater than steps 3, then this is an unfavorable process because the delta H is greater than 0. And we'll talk about this more when we get to entropy later this semester. But for now, if the steps 1 and 2 are greater than step 3, the unfavorable process it's an unfavorable process if delta H is greater than 0. If steps 1 and 2 are less than step 3, the reaction is favorable. So next we're going to talk about intermolecular forces. If you remember from Gen Chem 1, like dissolves like, how nonpolar dissolves with nonpolar and polar dissolves polar. The same concept here is similar, where two compounds are miscible or soluble with one another if they have like substances. So usually on an exam, what they'll do is they will give you a molecule and they'll ask you whether or not it's dissolved and if it's mixable with water or maybe a nonpolar solvent. And so can you tell? So it's marked by the presence of the OH. For example, for this one on the bottom left, it has 2 OHs. So we'll be able to mix this in water. Compared to the molecules on the top, what's going to happen is that these guys are not going to be able to mix with water because they do not have these OHs. However, they will be able to mix in a nonpolar solvent, like say benzene. So here are the important formulas for this unit. They might seem familiar to you in your class, but this is a good refresher. I'm going to point out some couple of tips that is pretty helpful. So for one thing, first, it's really important to read these carefully. For instance, the difference between molarity, which is capital M, it's going to be moles of solute over the liters of solution. Molality, on the other hand, is going to be moles of solute over kilograms of solvent. So it's definitely good to keep in mind what the problem is asking you to solve for. So the difference between the two, is, please, y'all, please don't change the slides. Thank you, appreciate it. So with this, molarity varies with temperature. Usually if there's going to be a lot of heat involved in your experiment, you don't want to measure molarity. However, it's easier to measure the volume of the solution than the mass of the solvent. Molality, on the other hand, is temperature independent. The percent by mass is in this formula. Usually you'll see X% of the ABC, like a solution of a compound. And what's going to happen is that it's the grams of solute over the grams of solution, which is made of grams of solute plus the grams of solvent times 100. So this is temperature independent, so there's no need for molar mass in this situation. And the mole fraction, oh, okay, the slides are not here. Okay, I think sorry about that, y'all. I think the slides should be back now. So, okay, so as I was mentioning, percent by mass, if you have like, say, like X% of AB, let's say that you have like 20% of like methanol solution, it'll be 20 grams of methanol over 20 grams of methanol solution. And we know that the solution is just the grams of solute plus the gram of solvent times 100. So grams of solution is usually 100 grams unless it's indicated by the problem. This quantity is temperature independent, and there's no need for molar mass in this case. The mole fraction is essentially just the fraction of solutes, the fraction of the quantity over the total quantity. So for instance, the mole fraction is going to be moles of solute over the total moles of solution, and then the mole fraction of solvent is going to be moles of solvent over the total moles of solution. And since these two quantities are fractions, it kind of makes sense why it would be equal to 1, because 1 is your whole number. And this quantity is temperature independent. So a couple tips that I can give you for this is that watch what you're solving for. So let's say you have an instance of you have in the problem given the density of your solution and the volume of the solution. However, when you solve it for mass, pay attention to what you're solving for, because you're able to find the mass of solution, not the mass of solvent. What a lot of students do is that they'll just go ahead and just take this number found, the mass of solution, and plug it into the molality formula. But remember that molality is over kilograms of solvent, not solution. So what you want to do is that you need to subtract the grams of solute from the grams of solution. And kind of that makes sense conceptually, because if you look at this diagram down here, the solution is made up of the solvent and the solute. So it makes sense that subtracting the grams of solute from the grams of solution after you found that quantity, the mass of solution, so that's how you get the mass of solvent. Okay. So there's another quantity that you can that is also measured. Percent means parts per 100. Therefore, instead of multiplying by 100 for percent, multiply mass fraction by 10 to the power of 6 for parts per million. Let's try not to change the slides, please. Thank you. And by 10 to the power of 9 for parts per billion. Okay, go back. So as I was saying, yeah, so a friendly reminder for the people that joined, please don't change the slides because it affects the view for everyone. Thank you. So as I was mentioning, so if you were to find parts per million, you would take, the slides will be uploaded the slides will be uploaded on the SSC YouTube website. So you can go back to that tomorrow morning so that you can get the information that you missed. So ppm is mass of solute over the mass of solution times 10 to the power of 6. ppb, on the other hand, is going to be mass of solute over mass of solution times 10 to the power of 9. Okay, so now we're going to go ahead and take a little break. I'll give you all like 2 minutes to just really consolidate your notes, and then we'll work on the slides. Okay, so we're back. in a little different window. So I'm going to go ahead and see. Okay, so let's talk about the factors affecting solubility. Can you all see my screen, by the way? Just double check. Yes, okay, cool. Thank you all. Okay, cool. So as I was mentioning, now we're going to talk about the factors that affect solubility. So when you're talking about the factors that affect solubility, there are a couple things to keep in mind. Primarily temperature and pressure are the really big ones. So temperature has varying effects with solids, and usually increases solubility, but it decreases solubility for gases. And you can take a look at this table on the top left. So you can see that the solubility versus temperature of a variety of salts, they have different patterns. It's a bit unpredictable. For gases, however, this affects dependent on whether or not the heat of solution is endo or exothermic. So gases are exothermic, and we'll talk more about this later. But since heat is a product, increasing temperature will shift equilibrium to the left towards the undissolved. So therefore, this will affect the rate temperature with gases. Next, we're going to be talking about pressure. So pressure significantly affects only the solubility of gases. And this kind of makes sense because think about when you're drinking like Coca-Cola, for example, right? So you have the Coca-Cola in your can, and what happens is that if the gas is like super present, like carbon dioxide, if it's super present, then you get that fizzy feeling to your drink. And it's kind of the principle here. And it's further explained by Henry's law, which is that the solubility of a gas, C, is directly proportional to the partial pressure of the gas, P, over the solution, where K is equals to the Henry's law constant, and it depends on the compound. So because this K is constant, we can shift and create another equation to the bottom right. The C1 over P1 is equal to C2 for B2. What this will look like in problems is that they can either give you 3 of these variables and you're identified the 4th one. So what you do is just make the 4th variable your missing variable and solve for X. Next, we're going to talk about Rule's law, which is the quantitative expression of the solution vapor pressure, where P solution, according to the picture on the left, is the observed vapor pressure of the solution is equal to the mole fraction of the solvent is equal times the vapor pressure of the pure solvent itself. And this can, in many cases, this can be shown with more added gases. So as you see on left here. So if you have more than one gas in the second one, in like the solution, you can kind of add them together, and it'll give you a P total at the bottom right shows. So I'm thinking I need to go ahead and just switch back to Blackboard. 1 second, because I wanted to do a little bit of demonstration here. Just give me 1 second. So if you're just joining, please don't change the slide as I kind of walk you all through this PowerPoint. Really appreciate that. Just 1 second. Okay, so like I mentioned, please don't change the slides for those that are on your live session. So what's going to happen is that this is how you read this graph. So at the bottom, you have your x-axis. So what do these numbers mean? Well, this means the mole fraction of gas A, and the mole fraction of gas B. This is when, at the start, the mole fraction of A is 1, and on the at the other end, the mole fraction is equal to 0, and vice versa. The y-axis gives you the pressure. It will usually be in ATM. So what do these lines mean? So the first blue, the PB right here, this is the pressure of gas B that's contributing to the solution. A is going to be the pressure of the gas A, how much it contributes to the solution. Like I mentioned, y'all, please don't change the slides. Thank you. So with that being said, so there are a couple key points that I wanted to point out. So what happens is that the pressure of both lines, right? This line, so this point, and then this point, it'll add up to give you this point. And this is what this line says. The pressure of the total solution is made up of the pressure of A plus pressure B acting on it. So when this solution is at equilibrium, which is in this middle, which is right here, and then you have right here. So this is 0.5. This is 0.5. Now, where does that correspond? Well, if we look up here, right here, and then right here. Notice how the pressure of line A is higher than the pressure of gas B at this point. So because of this, we can say that pressure A exerts more contributes to more pressure of the total solution than pressure B, gas B. So therefore, we can say that pressure A is the more volatile gas. Okay, so go ahead and switch back to the other slides. So go ahead and just quickly share my screen. Okay, cool. So now that's being done, let's talk about colligative properties, right? So colligative property, it's the properties that depend only on the number of solute particles in solution and really not the nature of the solute itself. There are three to keep in mind. That would be, first, let's talk about the vapor pressure lowering. So what's going to happen is that adding a solute blocks the surface site for the solvent to escape to the vapor phase, lowering vapor pressure. So what does that mean really? So if you look on the model to the right, we see these two beakers with the pure, and then we have a solution, just the pure solution, and we have one with a solute as well. So notice how in the pure container, there is a lot of gas being evaporated, because when something turns into a gas, it must go from liquid to gas, and when it does that, extra heat has to be added to the bonds, and there has to be space for it to evaporate, right? However, in this left case, there is no solute blocking the surface, so the particles can easily evaporate. However, when you look to the right, there are solutes that are blocking the space, as denoted in red. What this means is that there's going to be less gas molecules that escape, and so therefore we can say that there's going to be a decrease in vapor pressure, because pressure is just the measure of gas collisions, and if there are less gas molecules, there's going to be less collisions. Therefore, leads to a vapor pressure to lower. Next, we have boiling point elevation and freezing point depression. So let's relate back to that that example. So on the left here we have the surface unblocked. On the right we have the surface blocked. So because this right is blocked, on the diagram of the right is blocked by the solute particles, you're going to need more energy to make those liquid molecules escape to gas. So to compensate for that extra less space being able to convert the liquid to gas, you're going to need to add more heat. The boiling point temperature is where vapor pressure equals to atmospheric pressure. Adding a solute increases this because more energy, more effort needs to be added in for those liquid molecules to escape to gas. So when we talk about freezing point, when we're talking turning from liquid to solid, there's going to be more space for for ice to form, right? So if the solute molecules are blocking that, therefore there's going to be less space for it to block. I mean, there's going to be less space for it to form. Therefore, we can say that it's going to be needed a colder temperature to freeze. Therefore, we can say that the temperature must be lowered because the solute inhibits the formation of the lattice. Next, we have osmotic pressure. And what osmotic pressure is that it's the pressure required to stop osmosis or where the movement of water through a semi-permeable membrane. And this makes sense why this is a colligative property, because many of you may know from previous science classes how diffusion works of water specifically works from high to low concentration. And if there's solute, it's going to change the concentration in water and will flow in the direction towards isotonic, or the same osmotic pressure. Here are the formulas that you can kind of need to know for the exam. I'm not going to go over most of them, but I'll give you some key pointers. Remember, so we said that boiling point always increases, or there's an added change in the temperature, right? So if you get confused about this equation, like where the TB is it what's it called? Is it boiling point of solution minus the boiling point of the pure solvent, or the other way around? Just remember that you always want to have your TB have to be higher because it's a boiling point elevation. Same with freezing point. If you look on the equation to the left, the TF is equal to TF naught minus TF normally. You know that the freezing point of a solution with a solute added in it is going to be lower because of the inhibition of the lattice formation because of the solid molecules. So therefore, that's why TF of the solvent minus TF is just minus TF gives you that formula. There's something else to keep in mind is the Van Hoff factor. The Van Hoff factor is 1 for non-electrolytes and it increases for electrolytes based on the number of ions. So what this means is that when we're talking about a colligative property, we're talking about like how much solutes there is, right? So something like calcium chloride or even salt, really, NaCl, will either elevate the boiling point more and depress the freezing point more compared to non-electrolytes. This is why sometimes you'll see people, especially during like the last winter day where we had like snow or ice form, sometimes people would sprinkle ice on there to lower that freezing point. So because you want it to freeze at a lower point, you don't want it to freeze to a higher point, you know? Couple things to keep in mind as well is that for the temperature of the freezing point and the boiling point, there's going to be small m, which is molality, and versus osmotic pressure on the right is going to be big M, which is molarity. Okay, so that will be it for chapter 13. Now we're going to move on to chapter 14, which is the chemical kinetics. So reaction rates, not all the reactions occur at the same speed. For example, the rusting of iron versus the conversion of diamond to graphite. That's going to be done in 2 completely different speeds. And outside of chemistry, we kind of see this too in everyday life, where when you're cooking food, you see the reaction going place. You see the food cooking, or even when you're freezing food to preserve it from rotting, that's also a reaction that takes place. A couple of factors relate to increasing reaction rate, but before we talk about that, I think we should talk about the collision theory. So collision theory explains why the reaction rate is proportional to the number of collisions per second, and the rate is defined as the percent of collisions over the second. So there are a couple of things you kind of need. If you look at the molecule on the top right, it's gonna they're gonna need 2 things. So if a reactant is moving too slowly, it's not gonna react because they're gonna like not have enough speed to run into each other. So usually that's why you kind of need heat for kinetic energy to like really accelerate those particles. Next, you have the reactants. They have to face the correct orientation or else they won't react. However, if you both have the correct speed, that's the kinetic energy or the heat, and you have the correct orientation, therefore you'll have the chemical reaction. So the unaffected collision, and when those two happens, something called an effective collision happens, where a collision of reactants result in the product. On the chart, there are 2 things there are 2 graphs right here. So what you need is you need the minimum activation energy, which is defined as if you look on the exothermic reaction, the start of the graph to that little asterisk, which is called the transition state. So you need to overcome that energy, and that's when you would supply something like a catalyst there. Something to keep in mind as well is that the net energy released for an exothermic graph is just going to be the difference of the end versus the start of the reaction. So on the right, for an endothermic reaction, what's going to happen is that what's going to happen is that you also need to overcome this, but the graph is switched this time. So if you notice, an endothermic graph is just an exothermic graph, but it's reversed, and that means the activation energy is different as well. Instead, notice how for the reverse reaction, if you're flipping the first one, it's going to be a lot. You have to overcome that hill. You can think of it as like a roller coaster, where when you have to get to that apex of the roller coaster before you finally go down, and that's what essentially the activation energy is. So factors that going back to this slide, factors that affect it are, and you're increasing the reactant concentration. And when you increase the reactant concentration, what's going to happen is that if you have more reactants, you're going to have the possibility of more molecules. And more molecules mean that they are able to collide to each other. They have a better chance of colliding and a better chance of performing the reaction. Next is increasing temperature. Like we mentioned, this is going to affect the speed at which they collide, and speed is a requirement for the reaction to occur. The same principle with increasing reactant concentration, also the increasing surface area as well, making more space for those reactions to collide. Reactants to collide with one another. And finally, the presence of a catalyst, which lowers the activation energy, that barrier or that tip of the roller coaster that you have to overcome. So it's possible to follow the progress of a reaction by measuring the concentrations of reactants or products over time. So if we take a look at this, at the bottom left, we have reactant A turns into product B. What's going to happen is we can say that the negative change of concentration of A over time is equal to the concentration of change of B over time. And why is the reactant negative? And then why is the product positive, you may ask? Well, it's because if you think about it, product A is going to be converted to product B. So therefore, it makes sense to see why there's a negative sign in front of A, but not the product forming, which would be positive gain concentration, as on the right. If you're talking about stoichiometric ratios, you can take that into factor as well, where you have the picture on the right, A with the little letter followed by the big letter. So the little letter is the coefficient, the stoichiometric equation. A good tip to keep in mind from Gen Chem 1 is you should probably check before the equation is balanced, because sometimes they like to trick you doing that. But essentially, you just take the negative reciprocal, the -1 over that value, and then times the concentration of A over T, and you just do that for the rest. And once again, keeping in mind that the reactants are negative, have a negative sign in front of them, and the products have a positive sign in front of them. Adding on to this, we can actually find the rate law, which is the equation relating rate of reaction to the concentrations of reactants, where the general form of the rate law is the rate is equal to K, which is a constant, finding A to the power of X, B to the power of Y. And so K is the rate constant, and X and Y are found experimentally. So it's a good thing to remember is that you don't put X and Y based on the stoichiometric coefficients. I can guarantee you that there will be an answer choice on your test where it's going to be the X and Y exponents are going to be the stoichiometric coefficients, and that's how they want to get you, trick you. And so how do you find that? If you may be wondering. So let's say we have this problem, right? This is an experiment that was done in a reaction, and we have this data. And so from this reaction, the 2NO plus O2 turns into 2NO2. We can write that the rate law is K times the concentration of NO to the power of X times the concentration of oxygen to the power of Y. So we have to do a bit of math here. And I posted my work on the next slide. And it's a lot, but we can go through it together. Can you all see my cursor, by the way? Just making sure. Yes, okay, perfect, beautiful, okay, thank you. Okay, so essentially, let's go through this, right? It's a lot, but let's break it down together. So first, what you want to do is that you want to set your rates equal to the initial rates equal to your concentration, or like your NO and then your O2. So you want to do that for 2 experiments. And you can find any of these coordinates first. Well, the way I would first start, not coordinates, the exponents first. So first, I will write out the rate law, which is equal to K to the concentration of NO over to the power of X, concentration of O2 to the power of Y. So what happens is that we're going to have to arrange this sort of way in order to get the other exponents to cancel out. And what that means is I'm going to first look for an experiment that has the same, if you're doing a two concentrations experiment, which means that there's 2 reactants, all you have to do is just find 2 experiments. They have the same concentration for one of them, for one of the species, and the other one's different. For example, the first one, I notice if I look at experiment 3 and experiment 2, the NO concentration is the same. And so on the right here, the NO2 concentration is the same. And so for what happens is that when I set y for the y here, or the O2, the oxygen, I notice that they're not the same. And that's gonna give us a hint on how we're solve for. So with that being said, what's going to happen next is that we set equal to the rate, right? So in experiment 3, we take that experiment right here, and then we put the experiment 2 over there. So once that happens, you kind of want to like simplify it using your calculator. If you simplify it on the left, it's going to give you 2, and on the right, it should give you 2 to the power y. And then when you solve for exponent rules, y is equal to 1. So you may be asking, what if I flip the experiments? Like, what if I put experiment 2 over experiment 3? Well, it should give you the same value, because no matter how you do it, you'll always get the same answer. It depends on, you just make sure you match the values of experiment 1 with experiment 1. Don't get them confused up, say like 2, for instance. Finding the other variable. So we said that our y is equal to 1 up there. So now we have to go ahead and solve for the other one, which is, for here we see I use experiment 2 and I use experiment 1. So what's going to happen here is that I set them equal to each other. I found that on the left side with the rates, I get 4, and then that equals to 2x, and x is equal to 2. Sometimes you may get something like 1 is equal to the base, like let's say sometimes you'll get situations so before you get to like 1 or something, so it will be 1 equals to 2 to the power of x. But what's going to happen is that anything that is to the power of 0 will give you 1. So that's what you would do. So the answer to that would be 0. Okay, so when we find those two variables, we have the rate law is equal to k is equal to NO2 to the power of 2, NO2 to the power of 1. Is the 2 value where you said your n is like? Yes, that is correct. Okay, so with that being said, next our step is to find k. And how do we find k? We find k by plugging in the values from an experiment. So now that we have our rate law at the bottom here, we just go ahead and take any experiment. For this example, I use experiment 1 as I highlighted in blue up here, but you can use 2 or 3 whenever you want, if you want, and they'll give you the same answer too. So I took rate law is equal to k over NO to the power of 2 times O2. So that's the rate law that we found. And so I just go ahead and plug into variables. And when I solve for k, I get this value, and I get these units as well. So how do we find units? You may be wondering. So to solve for k, what we had to do was that we had to move the variables on the right to the left, right? So when we divide by the numbers, on the right, as I did here, we can think about it as like dividing by the units too. So this m squared comes from here because you're taking the molar concentration to the second power, then taking the molar concentration of the first one from this section here, from the oxygen gas. And so when you divide it, you keep change flip, and then the m cancels out, and you get molarity to the power of -2 to the power times seconds over to the -1. And that's how you can find the units. And if you multiply it by the k constant, a good way to check if you have the correct units or not is that you can multiply it by the value of the molar concentrations here. So take this value times m squared times m1, and you should get the y unit, which is the initial rate, so just m over s. Okay. If you do this for all the order of the reactions, you can get these units too. I'm not going to go over them, but it's something that you can intuitively get. If you're that kind of person that likes to intuitively like see it happen, then this is for you. But if you like to memorize it, go for it. Alrighty. So our last topic before we go out into the breakout rooms is going to be this. We're going to be talking about the integrated rate laws and the half-life. So this is a lot, but we're going to go over them step by step. So when you take the rate laws of the 0 in the first and the second order, I usually don't see third order reactions out there, so that's why it's not really talked about. You can get these formulas. I'm not going to go over how to derive them because we will be here all night, but some formulas you should know are this formula, and this formula. So what's really important is that you can find that you can see a straight line plot to determine the rate of constant. So what I mean is that for this one, for the 0 order reaction, you always get a negative slope, but you have to pay attention to your x and y axis. So for the zero order reaction, there's going to be concentration over time. And then there's going to be, for the first order, it's going to be ln of concentration over time, but also get a negative slope. So a good tip to keep in mind is that you want to pay attention to what are the units your y and x-axis is. The third one is going to be your only positive one. It's going to be 1 over your concentration over with a time x-axis, and the slope will give you positive k constant. So what this potential question that can give you is that they can give you a set of experimental data, or for an experiment they give you like 3 graphs, right? And so you're supposed to identify like which reaction it is based on the graphs. So you would look at the y-axis and the x-axis, and then the direction of the slope that's going in, and you can see which one matches. Yeah, and so we will have practice problems on that. So let's talk about, before that, we can talk about the units of K, which is if you do the derivation that we talked about the previous slide, that's what you get. So let's talk about half-life. So half-life, if you see the top right corner, it's going to be the half-life times it take for 1/2 of a substance to decay. So for example, if a half-life of a substance is 400 seconds, after 400 seconds or 1 half-life, half of the entire substance remains. So let's say that we have 100 grams of a substance. So after 400 seconds, which is 1 half-life, we'll only have 50 grams of that left. However, keep in mind that the half-life takes a time for half of substance to decay. So half of the 50% is 25%, and that's what it's going to have between 2 half-lives. So after 800 seconds, 2 half-lives, 25% of the entire substance remains. So the half-life stays the same throughout, because you would think that the half-life would be cut in half or something instead of like 200 seconds. That's not the case, and that's where students usually kind of pull the trap for. So it's always a constant for the radioactive substance. Next, we have the if we do it again, we have after 1200 seconds or 3 half-lives, 12.5% of the substance remains. And where do you get that 12.5? You may ask. Well, we get that from taking half of 25%. So half of another half-life, 25 divided by 2, gives you approximately 12.5. Yeah. So this material may not be covered yet in your lecture, but it's good that you are getting the preface right now. So it looks familiar when you guys go back to class. Okay, so that is all for the review questions. We're gonna go ahead and take a quick break. We'll also be able to answer questions, but after the break, we'll be answering the rooms. We'll be working out practice problems in breakout rooms. Work on this problem together. And I'll give you a few minutes to read this problem, and then we can talk about it. Okay, so let's first ask what the problem. Let's look at what the problem is asking us to do. So if we read the problem, a solution is made by dissolving 180 grams of ethylene glycol, given the molar mass, in enough water to make a 1 liter solution. The density of the solution is 1.24 grams per milliliters. What is the concentration of the solution expressed in molality, percent by mass, and parts per million? Okay, so it's a lot to break down, but let's go ahead and just find what we know first. So, what I would do is I would start out by writing the formulas here. So let's go ahead and tackle like the difference between molality and molarity. So we have big M, which is going to be moles solute over liters of solution, right? One second, you all. My board is not working. My open board is not working, unfortunately. 1 second, I should be able to work now. Okay, perfect. Cool. Okay, so let's take a look at this, right? And so little m is going to be moles of solute over kilogram of solution. And those are, kilogram of solvent. So let's think about how we're going to approach this problem. So what I would do is I would label like everything. So this would be, if it's dissolving ethylene glycol into enough water, so that would be, let's say this is the solute, right? And then the water would be the solvent, because that's our medium in which we're dispersing the ethylene glycol in. Okay, so our next step, what I would do in this case is I would kind of work with what I have. So we can go ahead and find molality, and to find our moles of solute, what we can take is we can take our 180 grams of ethylene glycol. I'll go ahead and denote that like this. And then using dimensional analysis, we can turn it into the moles of ethylene glycol. We're given the molar mass, which is 62.07 grams over 1 mole. And what's going to happen is that when we solve for that, we get around 2.899 grams of ethylene glycol. Okay, so well, we're kind of stuck with what to do next. Well, we have our mole of solutes, right? But we don't have our kilograms of solvent. But I'm given a few key facts in this problem. I know that the density of the solution is 1.24 grams per ml. And I know that we have 1 liter of solution, but in this case, what we want to do is that we want to have it to have equal units, right? Because this is an ml, we want to have equal ml. So 1 liter turns into 1,000 ml. So we get x, and when we solve for x, we get x is 1240 grams of solution. So a common pitfall here is that what you're going to do is that you're immediately going to plug this into your equation, into the molality equation like this guy, like this one. But however, look at this. It's kilogram of solvent. What we solved for was grams of solution. So we're going to do that extra step. We're going to need to do an extra step. What's going to happen here is that we're going to take, we know that the solution is made up of the solute and the solvent, right? So we can say that gram of solution is equal to the gram of solute and the gram of solvent, because those are the 2 parts of the solution. So when we plug in, when we do algebra, we take 1240 grams, which we solved for up there. We're given that there are 180 grams of the ethylene glycol solute, and we have this left, right? And so what's going to happen is that now that we have grams of the solvent, we can say gram of solvent is equal to 1060 grams. Any questions so far? Okay, cool. No questions? Then I'll keep going. Cool. Okay, so next we have our 2 puzzle pieces, right? Molality is equal to the mole of solute, right? Which is going to be 2.899 over the kilogram of solvent. So turn that into kilograms, which is that. And what happens is that we get our molality is 27.35 mole. So I'm going to go ahead and write that on here. Any questions so far? Okay, if not, let's go ahead and do percent by mass. I'll do that in a different color. Let's see, some blue. So if you remember from the PowerPoint, the percent by mass is the grams of the solute that you have. So in this case, we have 100. That's not good. Okay, 180 grams, right? of ethylene glycol. Oh, okay. Ethylene glycol over something else. And that something else is going to be the grams of solution that you have. In this case, you have a total of 1240 grams of solution. So that's going to be 1240. And then times 100. And when you put that in your calculator, you'll get that it's 14.5% by mass. Wouldn't the equation from LV be 2.899 divided by 1.060? Okay, let's see. So we have the grams, right? Divided by, yeah, you bring up an extra point. Yeah, good point. So a good thing to remember is, check your basic math. So yeah, excellent catch, Murtaza. Thank you. So put this over here. And then we do that, which is you just move the decimal wrong, which is like that. Thank you for catching that. Yeah. So like I mentioned, be sure to check your work because you don't want to like get the really hard math or the science done and then get it wrong, something silly like that. Okay, cool. So let's talk about the parts per million. So parts per million is essentially the same part over here, like this percent by mass, times per million means 10 to the power of 6. And we get that when we solve that, we get 1.45 times 10 to the power of 5, which is that. So that would be your answer. So 1.45. Let's go ahead and just box that. Okay. Any questions so far? Okay, cool. If no questions, then we can keep going. So a student is given a solution that is 66% isopropyl alcohol by mass with a density of 0.74 grams per milliliter. The student is asked to report the concentration. What should you report as molarity molality? The molar mass of isopropyl alcohol is that much. So I'll give you all like a few minutes to read this problem, like attempt it yourself, and so we can talk about it in a little bit. Okay, so let's get started with this problem. Go ahead and just make my screen a little bigger. So, is it assumed that the solvent is water? Yeah, sure. We can go ahead and assume that. Okay, so let's do this. So what we know first is that we have this key fact, right? And so if you have a percent by mass formula, you can deduce that you have 66 grams of isopropyl alcohol go ahead and denote that over 100 grams of solution. Solution. Okay. What's going to happen is let's first remind ourselves what is molarity, right? So we know that it's mole of solute over liters of solution. Okay, so where is our solid, you may ask? Well, you can say that the moles of solute is going to be your isopropyl alcohol because you're dissolving the isopropyl alcohol into the water. So how do we turn that to moles? You go ahead and just take that grams and you divide by the mole mass. And when you do that, you get 1.09 mole isopropyl alcohol. Do that. Okay, so we have one piece of the puzzle. We have the 1.09, and let's determine how we can find the liters of solution. Okay. Well, if you look at the density, what they'll give you is that if you look at the molarity, right? I mean, sorry, not the molarity, the density, you get 0.74 grams per ml. Is equal to 100 grams of solution. Because you assume it's a because it's 100 grams of solution. When you do that, you get X, right? And X in this case is going to be milliliters of solution. And so I'll give you all a second to do that math. Okay, so if you solve for that, what you get is 135.13 milliliters of solution. Okay. So now that we know the milliliter solution, we can go ahead and convert that. So we take 135 by 13, divide that by 1,000, and they'll give you 0.135, and your molarity would be 1.09 divided by 0.135, and that would be 8.07. Is everyone good so far? Does anyone have any questions? No? Okay. So let's continue on. So our next problem is asking us to find molality. So if we recall to the molality formula of the other brown, it's going to be mole of solute over the kilogram solvent. So how do you find well, let's find grams of solvent first before we do any conversions. We know we have 100 grams of solution, and we also know we have 66 grams of the solute. So subtracting those two should give you the solvent, like the grams of solution equals 2 grams of solute plus grams of solvent formula we talked about earlier. And when we do this subtraction, what we get is we get 34 grams of water, which is our solvent. Converting that to kilograms, what we get is 0.034. And then if we take our mole of solid, which we found on the top part, we have 1.09 is equal to that. And when you solve for the problem, what you get is you get 32.0 molar. Okay, anyone have any questions on this problem? No? Okay, so for the molarity, I got 8.135. Then that's because you run it early. Yeah, it's pretty much because I think it's because we all run at different numbers. But if you get around there, it should be okay in your exam. But just go with just because of tidy reasons, I just go ahead and run it. But on your exam, don't run to the end. Yeah. Thanks for pointing that out. Yeah, you're good. Okay, so let's talk about 1 to 3. Which statements are true? So I'll give you all like a few seconds to think about that. And we can talk about it. Okay, so which statements are true? Percent by mass is temperature independent. We know that's true. Molality is temperature independent. That's true. Molarity is temperature independent. That is wrong. And mole fraction is temperature independent. So that's true. So as you can see here, the quantity that is not temperature independent would be molarity. Okay, let's move on to the next part. We're going to talk about factors that affect solubility or, temperature, pressure, etc. So if you want to sweeten a cup of tea, it would be easier if you stir up the sugar while the tea is... Give you a second to answer that. It'll be hot. Because what happens when you stir that syrup, or the sugar, is that the kinetic energy from the hot cup of water will be able to like attack the bonds in the sugar, so it will be to dissolve better or become more soluble. So pressure significantly affects which of the following substances? I'll give you a few seconds to answer that question. Yeah, so it'll just be gases. It doesn't affect solids or liquids, just gases. Below is a structure of vitamin C. Is the water molecule water, fat, or soluble? Give you all a second. And fat soluble is going to be something that's nonpolar. So, yeah. So, yep, that's correct. So it's going to be, this would be water soluble because it has these OHs. Like, see here? OH, OH, OH. Yes, so temperature affects all three. Okay, so let's do this problem 2.4. What is the concentration of, we can do that. What is the concentration of carbon dioxide while in sparkling water under a partial pressure of 4 atm? Carbon dioxide at 25 degrees Celsius. The Henry's law constant for carbon dioxide in water is at 25 degrees Celsius is 3.1 times 10 to the power negative 2 mole over liters times atm. Okay, so let's think about this, right? So we have a Henry's law constant, so we should probably use Henry's law. So that says C is equal to Kp. When you plug in the numbers, 3.1 times 10 to the power of 10 to the negative 2 times 4. And that will be, I'll give you all a second to type that into your calculator. .124. That's the answer I got. Yeah, awesome. Good job, y'all. Okay, so the solubility of carbon dioxide in water is 0.034 mole over liter at 25 degrees Celsius and 1 atm. What is its solubility under atmospheric conditions in which the partial pressure of carbon dioxide in air is 0.00027 atm? Okay, so I'll give you all like a second to work on this and we can talk about it. Okay, so let's take a look at what we have here. So we have one set of conditions and we have another set of conditions. And relating something to Henry's law, with this, we have this formula. We have C1, the initial condition of concentration, and the after change concentration and pressure. So let's kind of just plug in what we have here. So our first concentration is going to be 0.034 right, mole per liter, and our first pressure is 1 atm. Our second set of conditions is going to be 0.00027 partial pressure, 27, and then over x. We don't know what that is. So therefore, we can go ahead and just plug into our calculator and get our answer, which is going to be 9.18 times 10 to the power -6. Cool. Anyone have any questions on this? So I think the key here is make sure you label and plate everything in the correct spot, because you don't want to mess it up and then, get the problem wrong. Okay, let's move on. We have one of these graphs here, right? So let's go ahead and interpret this. I'll give you all a second to read the problem and we can talk about it together. Okay, cool. So hopefully you finished reading that by now. And we're going to talk about this. So we have two volatile liquids, hexane and octane, form a solution whose mole fraction versus vapor pressure sketch is shown below. An equimolar mixture of these two liquids is placed in a closed container. At equilibrium, the vapor above the pressure will be, and that's what we're asked to find. Okay, so let's go ahead and just kind of label what we have here. So we have hexane, right, which is the one in brown. So I'll go ahead and trace that on this graph. So when you get something like this, it's really hard to like match the graph. So I would say that this is here, this is the brown one. That's going to be hexane, and this do octane and like light blue. So we have like that, and that'll be octane. And so to determine like at equilibrium, what's going to happen is that we have here. So when the mole concentration of both species hexane, I'll say that hex, and then species oct is both equal to 0.5. And then let's compare where they are. So if we just draw it up here, hexane's that location, and then this guy is at that location. So what does this really mean? So if we look at this, right, at this rate, because the line for pressure of hexane is going to be above the pressure, above the line for octane, we can say that it's going to be greater mole percent hexane than octane. And this is because if you remember Rule's law, we have this right here. What's going to happen is that this will contribute more to that, what's it called? That pressure of the total solution. So which gas is more volatile? We can say that hexane is more volatile because the line is higher at equilibrium. Does anyone have any questions so far? Okay, cool. Sounds good. Yeah, so I think when I took the class, this was like pretty hard to understand because I think my professors like went a bit over too quickly. So I think if you have any questions on this, I would definitely ask. Okay, cool. Sounds good. Okay, so another section says colligative properties, but this part is a Rule's law problem. So I'll give you all a few seconds to read this, and then we can talk and tackle it together. Okay, so this problem asks you to what is the vapor is asking to find the vapor pressure of water of a solution made by dissolving a 230 gram of glucose. Molar mass is that number, and 570 grams of water, and the molar mass is that number at 35 degrees Celsius. And at 35 degrees Celsius, the pressure of water is 42.2 mmHg. Okay, so if we have two gases like this, what we're gonna do is it's a Rule's law problem. So we have one finding the solution, right, of the solution, and that's going to be equal to the molar fraction of the two gases right? Well, let's take the first gas. Let's take the substance. Sorry, the first substance, which is glucose, right? So the molar fraction of glucose, and then times the pressure times the pressure of glucose, right? Oh, sorry, y'all. My thing was kind of glitchy. So, well, that's for the entire solution, right? But the problem actually asks for us to find the vapor pressure of the solution of water, right? So we can say that P of H2O is going to be equal to the molar fraction of water times the pressure of water. Sorry about that. Go ahead and erase the other part so that it doesn't look too confusing for those. So that being said, are these going to be questions? Let's see. Let's go ahead and just dive into this problem. So to find the molar fraction, what we have to do is we have to first find the total moles of the thing, right? The entire solution, right? So let's go ahead and do that. To find mole of glucose, we have gram of glucose, right, which is 230, and we just simply divide by molar mass, which is that, because we've given the problem. And then that's going to be, let's go ahead and find the mole of water. It's going to be 31.67 mole of H2O. Just for time's sake, I'm going to be just rounding to these numbers, but just like when you're doing this on the exam, you should probably just keep them as is on your calculator. Okay, everyone with me so far? Any questions? Okay, if there are no questions, I'll keep going. Glucose is non-volatile, so we do not need it to include the. Yes, I believe so. Okay, so let's get started with the other calculations. So what's going to happen is that we have the mole fraction of, yeah, no worries. So the mole fraction of water, right? Of water is essentially going to be the number of just the mole of water, right, which is 31.67 over 3167 again, add to the mole of the glucose, which is 1.277. I'll give you all a second to do that math. So when I plug this into my calculator, what I get is the mole fraction of water is going to be 0.9612. And so just to plug in this formula, go ahead and do that in a different color. So we have blue right here. So this is going to be 0.9612. And we have this guy, which is 42.2. Multiplying it together, and we should get our answer. And what's going to happen is that we get the vapor pressure of water in this situation is 40.56 mmHg. Okay. Any questions on this problem? No, that's a lot of work, and it's a bit messy work too. Okay. Okay, cool. Oh my goodness, yeah. I know these exams are stressful, but I'm glad that this review session is helping you all. I'm going to clear this out, and while I've cleared this out to make space for the next one, you guys can take a look at number 2. Okay. So number 2, what is the freezing point and the boiling point of a solution containing that many grams of calcium chloride and given mole mass in the grams of water? You're given the Kf and the Kb values. Okay, so it's going to be a lot here. So let's go ahead and just find the freezing point first, I guess, because it's the first one. Okay, so if you remember from the slides, T, temperature of freezing, is equal to Kf Mi, right? So don't forget this I, because this, I can tell you on like the exam, one of the answer choices will have this number, but you didn't take account to the I value, and that answer will be the wrong one. So that's something to just a little heads up. We know that the Kf for water is 1.86, but we need to find molality. So let's go ahead and do that calculation really quick. So molality is going to be moles of solute over kilograms of solution, right? So let's find the moles of solute first. We know that our calcium chloride is, I'm going to write that smaller actually, because we need, I think this is fine. Okay, so like that. Grams of CaCl2 over, divide that by the molar mass, which is that, over 1 mole, is equal to the, so I3 here, or do we need the real experimental I value? That's a good question. So for this problem, assume I is 3, but I'd really like that you keep in mention that the I value is kind of lower because of those collisions, but assume for these problems that your I will just be like the formula. So in this case, calcium chloride is going to be 3 because 1 ion of Ca and 2 ions of Cl. So the I factor would be 3. But yeah, no problem. Good question. So when we continue our work, we have this mole of CaCl2. And what's going to happen is that we take this value, and then we divide it by the kilograms, of solvent. And our solvent is is the water. So what we do is that we just divide that by 1,000, and we get, let's see, and we divide that, we get 2.075. Okay, so I'll give you all a chance to do this a little bit, and then we can talk about it as a group. So you do plug in the formulas and try to come up with your own answer. Am I here? I think a couple people said that I glitched out. Okay, cool, perfect. I'll give you all a second to do that calculation. Okay, so for I for the I value, it's only for the ionic compounds. Yes, that is correct. So if you have something like that's covalent, let's say what's it called? Like C2H4, for example, the I factor is just 1. Okay, let's continue. Yeah, no problem. So what we get here is we get divided by 2.075. It's going to be 1.58. So we do 1.58 times 3, and that's going to be equal to, when you plug that in, and I, like we mentioned, I is 3 here. It's going to be 1.86 times 1.58 times 3. It's going to be 8.82. Okay. Any questions on this part? Are we all good? How are we all feeling? Okay, good. Sure. Okay, sounds good. If you have any questions, do let me know. But that's not yet, because we found the degree of change in freezing point, and now we have to go and find the actual freezing point, the new one. So it's going to be KF. The initial minus the true one. So when we plug the values in, the regular freezing point of water is just 0 minus TF, and then TF is negative 8.693. Any questions? Okay, let's go ahead and do the same thing. So you approach it the same way, but instead of using KF, you use KB. So KBMI, and on your exam, be sure to look at the right values, because in the heat of things, you kind of select the wrong ones, which is understandable. It's a lot to do when under a time constraint, but just be careful. And then I is always 3 because it's CaCl2, and we get 2.49, 2.46, or we can just round. Okay, and so TB, that's not done yet. We have to do something else. We have to set this formula. Minus the initial of the boiling point, so the old one. What do we add? Yeah, so I'm just setting them up. We do add, but when you solve for TB here, you just add 100. No, you're good. Yeah, it's a good question though. So if you ever forget which goes which, just know that you always end up with a higher boiling point, and you'll always end up with a lower freezing point, if that's what you're asking. Yeah. So freezing point is going to be negative 8.693, and then the boiling point will be 102.46. Okay. Any questions? Does that sound good, everyone? Okay, cool. No questions? Then we can move on. What is the freezing point and the boiling point of a solution containing... Oh, sorry, that's that one we just did. So what is the osmotic pressure of a solution that contains 23 grams of butyl alcohol dissolved in water to make 543 milliliters of solution at 25 degrees Celsius? So for this formula, since we're doing osmotic pressure, we need pi is equal to I M R T, and M is molarity, R is 0.08206, and the T is temperature in Kelvin. So we kind of know the other values, so let's tackle the hard one first. We need to find. So we do 23. We need to find molarity, right? So we know that molarity is moles over liters of solution. So let's go ahead and try to find our moles of solute, which is the butyl alcohol. We divide that by 74.12, and then we do 1 mole. Okay, and that's going to be 0.310 mole. And we get pi is equal to I. So since it's butyl alcohol, it's not an ionic compound, so it's just 1. M is going to be 0.310 over 0.543. We'll give you a tip. Kind of plug this into the calculator like it is. And then R is 0.08206 times 273 plus 25. Okay, so I'll give you a lot of that to plug in your calculator, but pi is equal to 13.96 ATM. The answer is ATM, yes, because yeah, because if you look at the R constant, the unit of R constant for pressure is going to be ATM, and so when you multiply everything out, it cancels it out. It's a really good idea to keep track of your units too. I didn't do it because of like just time and space constraints, but it's good to keep that in mind. Yeah, of course, no worries. Okay, so let's go to 2-4, okay, which says if 1 mole of each of the following substances is dissolved in 1 liter of water, which one is expected to depress the freezing point of the solution least? So, two things to keep in mind here. We're looking at freezing point depression and settling the least. So we know that according to this formula, F times M. So I depends on like the type of compound it is, right? So if it's ionic, you count the number of particles, and if it's not ionic, you just count it as one. So this is like the Van Hoff, right? What's going to happen is, let's go ahead and just identify the I for this element. So NaCl is ionic, it's 2. MgSO4 is going to be 2 because it's a sulfate and a magnesium. CaCl2, 3. CH12H22O11, that's going to be just 1 because it's not ionic. And FeCl3 is just 4. With that being said, let's go and take a look at the Paul mass. So it's expected to depress the freezing point of the solution least. So I must be the smallest value here, and the smallest value is I. I mean, is this one? D. Now, if it asks for something which would it depress the most, that would be FeCl3 because it has a Van Hoff factor of 4. Does that make sense, you all? Any questions? No questions, then we can go ahead and move on. So explain why the rate of disappearance of. But what if the Kf varies a lot for each compound? Yeah, so Kf is the freezing value of the solvent. So in this case, the solvent is water. So the Kf will always be what's that value we did up there? 1.86, I believe. Yeah, it's 1.86. Yeah, good question. Yeah, like that you're paying attention to the units because I think like what happens is that we just plug numbers in without thinking about them. But I really like that you're thinking about like what the numbers mean and the variables mean in the formula, which is awesome. Good stuff, y'all. So let's take it 3-1. So let's move on to kinetics. Explain why the rate of disappearance of carbon monoxide and the rate of formation of nitrogen gas are not the same in this reaction. Well, let's take a look at it. We have carbon monoxide, right, which is this one, and we have nitrogen gas, which is that one. And it's different because of their stoichiometric ratios. So because what happens is that per 2 mole of CO yields 1 mole of N2. So the rate of carbon monoxide consumption is more than the rate at which nitrogen gas is forming. So we can say different stoic coefficients. Does that make sense, everyone? Okay, cool. Next, from this formula, it was found that the rate of N2 is that number. Okay, so write the general rate formula for this reaction. What's going to happen is we take that formula. So we take the negative for the reactants. We take negative 1 over the 4, and then we take NH3, and then we do this, and then we set that equal to the rate of the oxygen to take the coefficient of that. And this is due 1/2 over N2. And notice how the reactants are negative and the products are positive, because that makes sense conceptually, because NH3O2 react to form the products, so it makes sense that as the reactants are decreasing, more product is formed. So if you ever forget like which is negative, which is positive, just think about the equation and what it really means. Okay. So we have that, and then we have H2O. Okay. Cool. So that's one part of the problem. Any questions on this? No. Okay. So B asks at what rate is water being formed? Okay. So we have 1/2. That's an N2. So let's take this, right? You can do, well, no, we have in this problem this, right? So we're given this, we know that the change of that is N2, and then we know that what's it called? And we're asking to find what? The rate of water formation, so it's H2O. And then we just set that. We take from our general rate reaction formula we wrote above, take those two parts. You can omit the other ones because we don't need them at the moment. And let's go ahead and find the rates of formation of water. So we are given this value in our problem, and we are given, we're asking to find this, right? So, and when we solve for x, we get 1.05 mole per liter. Excellent. Anyone have any questions? Mole per liter. Okay, if there's no questions, we can continue on. At what rate was ammonia being consumed? I'll go ahead and let y'all work on that problem, and then we can talk about it in a little bit. It's the same way you would approach the previous one. Okay, so the way you would approach this is that you take the formula for, well, we're asking if I'm ammonia, right? So ammonia, and the equation is this, is equal to the something that we need. So what do we have in this problem? Well, we have N2 because it's given the problem. And so once we solve that for x, we plug in what we know. And what number do we get? Well, we get x is equal to negative 0.7. And that means that it's decreasing at a rate of negative 0.7 mole. Does anyone have any questions? Okay, if not, then we can keep going. Okay, so this problem is determining, do you leave the negative sign because we already know it's being consumed? That's a really good question. So I would say it depends on what the problem is asking you. I would say that if it's just like, what is the rate? Just be like, oh, no, it's just that rate. But it's like, let me rephrase that. So if it's asking the rate of change, for example, it would be like, oh, it's decreasing at 0.7, right? But however, if it's asked for like, what's the value, you just put 7.7. Can I see the previous one? Yeah, sure. Does that answer your question a little bit? I know that was a bit muddy, so let me know if you want me to re-explain that again. Okay, cool. Yeah. So yeah, of course. So it definitely depends on how you want to read the problem. Yeah. Yeah, and if you're ever confused on that, you can always clarify with your professors on what they want on the exam or what they expect you to. So it has been a while since I took the class, so yeah. So we have 3-3, which is assigned to study the following reaction and yield the following initial rate data. Okay, so this one will take a bit of time, but we can still do that. I'll give you all like a few seconds to read it and like kind of think about how you approach this problem. Okay, so let's get started on this problem. We're given write the rate law experiment. Don't forget K in the units. So let's go ahead and just write the formula, right? Y is equal to K, right? And then we have two concentrations, this. Now remember, we don't write two like this two like up here because that's like a big no-no. What we have to do is we'll do it with the canceling out the units way that we talked about in the lecture. I can tell you one of the answer choices will be like, oh, it's K times E to the power of 2 times F to the power of 2. That's wrong. That's like kind of like the low-hanging fruit, I would say. We actually have to do the longer way. Like just thinking tips I can give you. I would do these problems last because they take a bit of time. So let's find the rate law of experiment. So if you remember from the lecture portion, what I did was I found two experiments that have the same data, and then they have same data for one of the concentrations, and then the other one is changing. Now let's say if I had like three variables, let's say there was like an X right here with the reactant, what I would do is I would find two experiments that have two of the concentration substances the same, well, the third one changes. So that way they'll cancel out. For this problem, we only have two. So let's go ahead. It doesn't matter where you start with, you can find X or Y the same. So I'm just gonna go ahead and just like look at this, right? So I for my first glance, I see that 3 and 2 are the same. So I'm gonna go ahead and just select those. And you can also do like 1 and 2, which will do to find one of the other missing variable, but we'll get there when we get there. Okay, so when we set that, when we take these two experiments, we set them to the concentrations of each other, right? So this is the rate. We have the concentration of this, so the concentration, so say like the concentration of experiment 3, and then the concentration of experiment 2. Another tip you want to keep in mind is that make sure you align the correct values. For example, you don't want to like put experiment 3 on the numerator, and then like on this side you put concentration of the substance of 2 instead, because you'll get some wonky numbers. You don't want that. Okay, so when we set the rates to each other, we get 50.9 over 8.19, and what we do on on this side is that we take this side, right? So there's a K on both sides. Then we do E. We do the first one, which is E, which is to the power of, well, we don't know. And then we also for the Y we have 2 to the power of Y as well. And at the bottom for experiment 2, it says we have 1. Sorry. And then this one is going to be, let's see, according to our be that. Okay, so what kind of happens here? Well, if we look at the right side, this is going to be here. That's going to cancel out because they're the same thing. But when we have left over, we have this. You can go ahead and just say it's approximately 2. The K cancels out. Use this worksheet. Yeah. I haven't seen the test myself, so I can't really say, but you know, hopefully this is some good practice for you all. So this is going to be like that. So don't worry, Allison. You can watch the recording, and you know, hopefully your answers will be like will be answered. But you can also go to Pure Tutoring too in the library. They're really helpful. Okay, so anyways, going back to the thing, we have this is equal to 1. Anyone have any questions on how we got like our x is 1? Any questions y'all want to add? Okay, cool. Now we have this as 1. When the exponent subtract, yeah, that's a really good question. So so the question is when the exponent subtract. So when you have the same base, the exponent, you just divide it. So I think you're referring to like if they have the same base but different exponents, you subtract. But for this one, it's just you divide. Normally, you keep the base. Does that make sense? Because what you're thinking about is x a minus y, which is going to be x a over x y. Oh yeah, yeah. So I'll give you a hint. That's going to be important like later on once we talk about other stuff in Gen Chem. So do keep that back in your head. Okay, cool. So let's go ahead and find y. Okay, so we have x. Now we need to find some y. So we picked experiments 3 and 2. Let's do something different. Let's say that since the concentration of F is the same, what we did over here, let's do it on the X. So we do rate, I'm just going to do just rate, just to simplify things, experiment 2 over experiment 1. Then we have the same thing. So concentration of 2 over concentration of 1. So once you do that, what's going to happen is you do 8.19 over 2 is equal to, so no, you're good. No, I really welcome questions. Sorry to ask again. So the x exponents, that's a mouthful, would divide, wouldn't that equal 1, the one you simplify? So yes, that's correct. So notice how you just divide the base by the bottom. So 2 divided by 1 is 2, and then you just carry over the x. Does that make sense? Yeah. Cool. Okay. Do we not need to do the math of the x? Well, we are doing the math here because what's going to happen is that on the left side you have 2, right, from the initial rate equals to 2.00 and solve for x. And when you solve for x, we know that, well, if you take 2 to the power of 1, you'll get 2. So therefore, our x value is going to be 1 to make this equation true. Yeah, I think that's right. You're thinking of the same basis. They're different bases, but same exponent. Yeah, so that's the case with this one. Think of exponents all. Yeah, there we go. Yeah. Okay, cool. So moving back to this problem. Yeah, I'm glad you asked that question. Awesome. Because I know this is a bit confusing. Okay, so let's go ahead and do the next part. So going back to this problem, we get 1. Since it's almost 9, if y'all need to go for it. Thank you for coming, but if you guys want to stay back and watch me finish the problem, the packet, you can, but it'll be all recorded. So, so we have 1 here, and then we have an A here. Sorry, not A. We have X, sorry. And then we also have this guy, which is 2. Okay, so once we cancel out, like the problem up there, this cancels out. And then on the left side, we can just go ahead and call that 2. Then we have 2y, right? And so when we solve for this value, we get is 2. because we know that 2 to the second power gives you 4, so therefore y is equal to 2. Or you can just do log base 2, and that's essentially what I did. Okay, so I know that was a lot of work for a few questions. Does anyone have any questions so far? Okay, cool. So like I said, I want y'all to think about what you have to do next, and then we can talk about it.
Is it okay if we could go over the intermolecular forces and the relation to solubility?
I'm gonna try to erase this page so we can. Well, first before I erase the page, what's gonna happen is, since it's 9, if y'all need to go, go for it. But this session will be recorded. Yeah. So you can view the YouTube video once you're done. Let's go ahead and figure out how to clear all of this. Okay, so I think it'll take a bit for me to clear it. So I'm just gonna go ahead and just try to make some space for it, like down here. So we have this, right? We have from our formula, we get K is equal to what's this? E, right? E2 E1, and then we have F2. Okay, cool. So with that being said, in order to find the K, what we have to do is you just plug in the numbers for, just take an experiment, let's say experiment 1, and then you plug in to there. Okay, so once you do that, let's go ahead and just write it out here on the top. So we can say that 2 is equal to K 1, 1, and then F2. Okay. So with that being said, we've still been F4. So we get K is just 2. Now, on your test, the numbers probably won't be this clean. I just made it clean to show you the math and the process. Okay, so what are the units of K? K is going to be, well, let's figure that out. So we have, on the left side, we have units of M over S. And then on the right side, we have Km over M2. So simplifying that, Ms divided by M3, because we want to isolate the K by itself. We're going to get units of, let's see, Ms times 1 over M3, M negative 2 times S negative 1. Okay, any questions? That's going to be your units. So summing everything up, we have K is, this is 2M negative 2 times S negative 1. Okay, cool. Okay, so let's move on to these type of problems. Consider the data for the following reaction. A plus B turns into product AB, and we have different graphs, right? So what's going to happen is we have a negative graph of that, negative slope of that, and then a slope of here, and then this one, a ln of A over time, which is very curvy, exponential, and then we have 1 over this, the concentration of A, that. So from the PowerPoint, there weren't any graphs that showed any curves like that. Isn't that for second order? Well, let's go ahead and find out, right? So let's go ahead and, well, we know that there are no curves, so here, right? So usually for this kind of graph, so does anyone remember what a ln A over time graph gives usually? Does anyone remember from the review sheet? First order, yeah. So if it's first order, what kind of slope does it have? Negative linear. Yeah, so that's correct. So usually it would look like this. Because it doesn't match like that, because this graph doesn't match that graph, it's not going to be first order. What about the second order? Does anyone remember like what the graph looked like between a 1 over concentration? Oops, don't know why that's that. Positive linear, there we go. Yeah. My screen's glitching out, sorry about that, y'all. Okay, so because of that, these two graphs are wrong. You'll get this one. This will be your correct. And what does this graph correspond to? Does anyone remember? V0 order. Yep, there we go. So we can say this graph is 0 order. And I can go ahead and type that so you guys don't have to deal with my messy handwriting. So we know this is 0 order because negative slope K and A, concentration of A versus time graph gives a 0 order reaction. Okay, any questions on that? So on your exam, if you see problems like this, you can immediately eliminate any like curve graphs like those two, because no reaction order, at least the ones that we're focusing on, will give a curve like that. Okay, so our next problem is if the initial concentration of that, if A is 0.04 and the concentration of that is at 0.02 at 3 minutes, what is the value in unit rate constant K? So let's go ahead and tackle this one. So if you remember from the chart, A is equal to A initial minus KT. So we know this value, which is 0.22, is equal to 0.4 minus K, which we don't know, and T. T is always in seconds, so don't forget to convert that. 3 times 60 is equal to 180, right? And so K is equal to 2 point, oh wait, sorry. Yeah, K is equal to 2 point times 10 to the power negative 3. And what are the units? Well, if you remember, for the initial concentration, it's going to be m times s negative 1. That's really your answer. At what time is the concentration of A equal to 0.004 m? So let's go ahead and just take that same formula. 0.0004 minus KT. So we have, this is our concentration. Oh, sorry about that, I messed that up. This is not that. When we plug in our known variables, we get this. And we know K from the previous question, but we're missing T this time. So if we plug in K, 2 times 10 to the power negative 3, I'll go ahead and give you all the answer, which it will be T is equal to 18.9 seconds. We good so far? Any questions? Yep, okay. So the last part. We're almost there, y'all. Where do we get 0.04? That's a good question. So we got 0.04 because notice that 0.0. Oh, my bad. Apologies. Yeah, 0.04. But the answer should be t is equal to 18.9 seconds. Good catch. So this is going to be our initial, which you just plug in there. Okay. Awesome. Let's go ahead and just get through the last part. So our last question says that the half-life of a certain first order reaction is 3.6 hours. What is K? Okay, so let's break down what we know. We know that the first order reaction, according to the chart, is going to be half-life for a first order reaction is going to be 0.693 over T, yeah. I'm sorry, over K, my bad. Okay, so solving this, every time you see something in hours, always convert to seconds. So 3.6 times 60 times 60, that will give you K is equal to 12,960. Okay, so I'm sorry, that's for half-life. So that's T, that's not a K, that's a T 1/2. Okay. So we just plug in what we know now. 12,960 is equal to 0.693 over T. Well, when we solve for X, what do we get? We get K. K is this value. Okay. Yeah. So, how many half-lives have passed when the reaction is 87.5% complete? Okay, so this one might be a bit of a doozy, so if you all get lost, just do let me know. So we have, let's say that we have 100%, we have 100 grams of solution, right? 100 grams of substance. So the 100, the blue, it would be grams, right? So when half of that is decayed, we get 50. Yeah, 0.6993. Yeah. So if you derive it, you'll get 0.693. But the test won't ask. I don't think they asked on how to derive things, so it's just something you can memorize. Yeah, that's where we get the 0.693 from. So, yeah, of course. So when we go from 100 to 50, that's half of a substance, or that's one half-life, right? So that's one half-life. When we go from 50 to 25, that's going to be another half-life, because it's half of that the substance remaining, right? So it's one half-life. And when we go half of another half-life, we go 12.5. So that's one half-life. Right? So we can say that 3 half-lives have passed. So the answer will be 3 half-lives have passed. Hold on a second, my computer is buffering. Oh, there we go, okay. So we have half-life. So 3. Make that near. Does that make sense, everyone? So a common misconception here is that you guys just continue taking that, it's a bit confusing when we're talking about half-life. So it's the half-life of the substance that's remaining. So it builds on top of each other. Okay. So how long will it take for this reaction to be 87.5% complete? Okay. Well, how do we get this 87.5 number? Okay. So let's start from the top, right? I'm going to write this in red. So the red is the percent of the reaction that has occurred, right? So when something is 100%, 100 grams, that's going to be 0% of the reaction that's occurred. That makes sense, right? Because nothing's decayed, so 0% of the reaction has passed. the going from the what's it called? Going from 250, however, 50% of the reaction has passed. Because that makes sense, because half of the substance has decayed. Going from 100 to 25, that means that 75% of the reaction has occurred. Now, how did I get 75? Well, if I just take this amount of stuff that we're starting with, the 100 minus the 25, and the stuff that's left is 75, which is the reaction, how much of the reaction has complete. The blue represents how much is remaining. Does that make sense to you all? I know that's a bit confusing to get. So just let me know if that makes sense or not. Okay, cool, excellent. So when we go from 100 to 12.5, what's going to happen is that it's going to be 100 minus 12.5% complete. So that would be 87.5. Well, how did I get 87.5? Like I mentioned, you just take, if I have 100 grams of substance and 100% of the substance and only 12.5 of it is remaining, then that means that 87.5% of the reaction is completed. Okay, and does this number look familiar? Yeah, so it's actually this guy right here, which is in problem C. So how do we find this reaction? The short way is that, we have 3 half-lives, right, from that B problem. We just times it by the half-life of this substance, which is, we said that it was going to be, you can do it this way, you can do 3.6 hours, or, what's it called? Or like the 12,960 seconds. It depends on the quantity they're asking for you in. So what I did was I did in hours, so I did 10.8 hours. And so that's going to be the answer to this problem. That's the short way. There's also a longer way too, and I'll go through that quickly. So we know that the formula for this first order reaction, because it said so in the problem, is this, right? T. So when we do some deriving this formula, we get this part. Right? So think of A, this is like as the part, and this is the whole, right? And so you can think that whatever substance you have left over your initial is how many grams of substance you have left. And so we know that we have 12.5 grams of, so 12.5% of substance left. So we can see that this part is like that. This is in grams, but this is in percentage. So it's 0.125% is equal to E negative RT, and you just solve for T from here. And you'll get the same answer in seconds. I just should put that there. Okay. Alrighty, that's it for the end of the packet. Can you post the link for this link packet? PDF? Yes, it will be blank for your use on YouTube, the SSC YouTube website. So check back tomorrow. Tomorrow, at the end of the day tomorrow, it should be uploaded then. Yeah, sounds good. Anyone have any other questions? Yeah, thank you all for staying afterwards. If you have any questions, do let me know. And good luck on your exam. Yeah, of course. Yeah, thanks for coming, y'all. Take care. Good luck.